Okay, Ilaria.
Okay, good morning, everyone. So we are really fortunate to have Dr. Ryohei Nakatani visiting the University of Arizona. He will be visiting for 1 week. Ryohei got his PhD from the University of Tokyo in 2019 and is currently an overseas postdoctoral fellow from Japan. He's working at JPL in Pasadena, and he will be staying there until July of next summer.
Yes.
So Ryohei has done some of the most detailed simulations of photoevaporative winds, which are, at least for sun-like stars, those that are probably dispersing the protoplanetary material. But today is going to tell us something, a different story for disks around more massive stars. So Ryohei, take it away.
Thank you. Thank you for the introduction, Ilaria, and thank you for giving me an opportunity to talk about my studies. Since I have been working on since graduate school. Again, I'm Ryohei Nakatani, visiting postdoc at JPL. Today, I'm going to talk about studies of disk photoevaporation. Okay. So the big picture topic of this talk is protoplanetary disk dispersal throughout this talk. And this talk is composed of two independent yet related topics. One is my first self-consistent simulation of disk photoevaporation. I observed molecular photoevaporative flows in this simulation. So I want to talk about it, hoping it might be interesting for you. And the second part, I'm going to introduce a more recent study of mine. We made up a new disk evolutionary scenario that may help understand the origin of recently detected very old gas disks. And this study is uploaded on arXiv this week. So I hope this talk would be a good introduction for the paper. So I'm going to start with this, the overview of classical planetary system formation scenario from molecular class to planetary systems. So it starts with the gravitational collapse of the over-density region in molecular class, and it forms protostars and disk embedded in an envelope, and the envelope disappears after a while making planets inside the disks. And then finally, it ended up with debris disk or planetary system, depending on the dust mix. So in this talk, obviously, I cover the late phase of this scenario. And main topic of this talk is the evolution from protoplanetary disk to debris disk. And I summarized the basic difference between protoplanetary disk and debris disk. Also, they are not very definitive. Protoplanetary disks are young, less than 10-year-old, and gas-rich, and having optically thick dust, and dust mass is usually high, more than one Earth mass. And the debris disks are more than 10 million years old and gasless, supposed to be gasless classically, and optically thin dust, and the dust mass is lower than the Earth mass. So I present the motivation to study the disk dispersal. For example, gas accretion onto planets migration only possible when the disk is present. And planetary atmosphere chemistry and orbital instabilities are different before and after disk dispersal. So overall, disk dispersal sets the time limits for configuring a planetary system structure and the transition point into the late planet formation stage. So disk dispersal is an important problem overall for the planet formation scenario. And I introduced the critical time between protoplanetary disk and debris disk as 10 million years. And it's coming from multi-wavelength observations tracing both gas and dust, as summarized in this figure. So overall, the lifetimes are several million years for both gas and dust. And there's a very large uncertainty in the outer gas disk lifetime here, but it's currently thought to be of the order of 10 million years. So 10 million years is a critical point. And before that, primordial planetary disks are present. And then after that, there's only gasless secondary dust disk present. This is the classical view. And on the theory side, many disk dispersal processes have been proposed as not all disk mass goes into the planet, of course. So for example, stellar winds, stellar encounter, viscous accretion, photoevaporation have been proposed classically. And as this figure shows, viscous accretion and photoevaporation have the shortest dispersal time. So they are thought to be the most important dispersal mechanisms in early 2000s until early 2000s. In late 2000s, it was pointed out that MHD winds are also important in disk dispersal. So now viscous accretion and MHD winds and photoevaporation are thought to be the major internal disk dispersal processes. And they are the topic of ongoing investigations in the field. And to summarize, there are two ways to disperse disks. First is falling onto the star, and the other is stopping from the surface. And the viscous accretion works as the former, and photoevaporation works as the latter. And the MHD winds can work as the both. So, yeah, this is all of these are under development and the hot topic in the field. And my expertise is photoevaporation, and I'm going to talk about photoevaporation mostly in this talk. And in more recent years, it is found that the dominant dispersal process, disk dispersal processes, varies in time. In the early stage, MHD winds are dominant. The energy source of the MHD winds are gravitational energy of the accreting disk material. So this is favored. This mass process is favored, especially at the early stage where disk mass is high. And mass declines relatively slowly, like a power law. And eventually, the mass loss, the main dispersal process is replaced with photoevaporation. The energy source of photoevaporation is, of course, the irradiation from the star. So it's relatively, the mass loss rate is relatively constant compared to MHD disk rate. And usually, this late phase is associated with the inner cavity, and disk mass sharply declines, as this figure shows. And I found interesting this time-varying view of the major dispersal process. Qualitatively, with jet wind observations, for example, jet wind mass loss rates are quite high at the level that photoevaporation can not achieve. And in the indicator of inner MHD winds are detected preferentially in relatively young sources, and in more evolved disks where accretion rates drops and inner dust cavity opens, the line profile of wind indicators gets narrower. So it might trace the photoevaporative winds in this very later stage. Anyhow, I found it interesting that the recent theoretical model and recent new observations are qualitatively consistent, because I feel like we are getting somewhere about this dispersal. So that's it for the introduction, and I'm going to talk about my self-consistent radiation hydrodynamic simulation in 2018 now. So this is the basics of protoplanetary disk photoevaporation. photoevaporation is driven from the radius of 10% of the gravitational radius, approximately, and stellar extreme ultraviolet, ultraviolet, and X-ray are effective for driving winds. It sounds like a little bit complicated. There are three kinds of photons effective for photoevaporation, but the basic mechanism is the same. They just absorb the photons and eject some summarizing photoelectrons to heat the gas. The differences are in main absorber, and that differences are reflected in the cross sections of photon absorption. And usually, EUV and X-ray absorption cross sections are smaller than EUV cross section, and that means they can reach a deeper area of the disk and can excite dense flows with higher mass loss rates. And when it comes to modeling of disk photoevaporation, ideally we want to solve all of hydrodynamics, radiative transfer, and fluid chemistry, but it's prohibitively computationally expensive, especially including tens of heating, cooling processes, and hundreds of chemical abundances, and thousands of chemical reactions is disaster. So what we do instead is taking one of these three approximated approaches. The approach one solves the vertical structure of the hydrostatic disk, solving full chemistry, full equilibrium chemistry, and full radiative transfer. And second one solves hydrodynamics with looking up the temperature tape. And these tables are usually prepared by solving full radiative transfer and full chemistry. And the third one is similar to the IL method, but with reduced chemical network and radiative transfer. My study takes this approach number 3. And all of these 3 have pros and cons, of course. For example, the approach number 3 can include advection of chemical species and can get the energetically self-consistent structure of the disk. But it's computationally highly expensive. It can take a month's order computation time for one model. So it's not well suited for example, parameter studies and long-term disk evolution. Anyhow, it's important to understand which method is taken to interpret the results of each model. Again, my model extensively use this self-consistentness. And this table compares the incorporated physics in each of this photoevaporation model. And mine is the rightmost column, at the rightmost column. So basically it includes everything. And this is counted as a significant new development in the field, which I'm honored by a lot. And now people are trying to coupling non-ideal MHD with this self-consistent sound chemistry, radiation hydrodynamics model. And
why there's a no and yes both for the X-ray?
In my model?
Yeah.
I have 2 studies about.
Oh, okay.
Yes.
A is no and the B you included it. Okay,
Exactly.
got it. Yeah, yes. Yeah, I got it. Yeah.
That's all. Yeah.
Yeah.
So yeah, now this model is under development by coupling non-ideal MHD with self-consistent radiation. So I expect a significant development will come in this decade too. So as for my model, this is a setup, numerical setup. I placed the initially hydrostatic disk around the low mass star, and I solved the ray tracing for FUV, EUV, X-ray, and 2D hybrid radiative transfer for optical IR wavelengths to calculate dust temperatures. And this is coupled with hydrodynamics and can reduce the chemistry. In this model, I only use 8 species and 18 reactions, so quite much reduced, but now it's very much expanded to this level. But anyhow, I'm going to talk about this very reduced model for today. So now let's see the overview of my simulation. And this is the movie. This is the first view of the disk. And immediately after turning on the stellar light, photoevaporation starts. And in the optical thin region, winds are present, like here. And the optical thick region defines the steady disk part. And usually these two regions are sharply divided. And the hot temp.
Can you tell us about those arrows that were pointing inward? So this was accretion outside.
Oh,
The beginning of. I've never seen this movie. Super cool.
was there?
At the very
Oh,
At the very beginning. Yeah. Oh, yeah.
okay.
So we can see it again.
Right. This is nice donut.
Yeah.
Thanks. Well,
yeah, so they
maybe
Yeah, here.
Yes.
so they sort of start
Right.
getting back in for a little bit.
Yeah. Look at that. Yeah.
this one.
Right,
Yeah,
right.
yeah.
So they were inward.
Yeah,
Yeah.
I think this is just an initial transient, like,
Oh, okay.
yeah,
So
it's
it's
just a
not-
numerical effect because I don't include viscous friction in this simulation.
Okay.
It's because it's quite super long time scale,
Mhm.
so it shouldn't be.
What
effective.
time scale did you do?
I followed the simulation for 10,000 years.
10,000 years. Very short.
Yeah, very short.
Yeah.
And
All right.
it's not possible to.
A million years.
Yeah, it took I think a month to compute 10,000 years evolution. You know,
Wow.
even with that very reduced chemical network. So anyhow, that is the longest simulation in the self-consistent models anyway. Maybe if we expand the chemical network, it takes more time to follow the 10,000 years evolution. Well, anyhow, yeah, this is the basic view of photoevaporating disk and how my simulation looks like. And this is more detailed view. Here's density and temperature, chemical structure, and spatial distribution of dominant heating processes, and spatial distribution of dominant cooling processes. So high temperature region, like 10,000 Kelvin, is corresponding to EUV heated region. And the other hot region is corresponding to FEV heated region. And the EUV heated region is almost ionized here. And the FEV heated region has atomic and molecular flows like this. And ionized flow has a very high speed, like 10 kilometers per second, thanks to the high temperature. And the molecular atomic flows has a slower velocity, like sub-kilometer per second to a few kilometers per second. And here is a CO photodissociation front, and it about which CO is almost destroyed. So I think it's difficult to produce extended CO photoevaporative flows in contrast to H2 molecular flows. And this is a further detailed view of the chemical structure of the wind. The basic structure is understood by the PDL structure at every single line of sight.
So they are the molecular hydrogen. What is the velocity for those? Very low though, right?
Yeah, very
Yeah.
low. Yeah, this is subsonic as will be explained later. Yeah. Anyhow, at lower Coulomb density regions, hydrogens photoionized, and H2 dissociation front is present at the deeper layer, and CO dissociation front are present at the further deeper layer. And the molecular flows are excited in 3 steps. First, they are produced in the disk by a green catalyst formation. And it's conveyed to upper layers by advection due to photoevaporation. And here I show my test simulations where I switched off FUV heating at 500 years.
Is it the one there on the right, molecular hydrogen flow? Is that?
Yes, this is molecular hydrogen flow, and white part is atomic flow.
Yeah. The blue part is molecular hydrogen, and then
Yes.
H2 is the green.
Yes. So immediately after switching off FUV heating, they disappear.
Oh,
Molecular and atomic flow disappear. So it means advection due to photoevaporation is important to form extended molecular and atomic flow. And another key factor is self-shielding, because outer molecules are actually protected by inner molecules in the flow. So without self-shielding, this extended outflow cannot be formed.
But for how long can it be shielded?
Sorry?
How long does it shielded? It doesn't look like that long.
Yes, that's an important question. So it can survive only for a photodissociation time scale.
Which is very short, actually. If I could see that from there, yeah.
Yes. So they can survive only a crossing time scale equal to photodissociation time scale. So after they are launched, they can, how should I say? They are only susceptible to photodissociation. They cannot reform it's the molecules in the wind. So
Of course, yeah.
they ended up in the molecular. So if I trace molecular flow from the base to upper layers, there is a transition point from molecular flows to atomic flow. So it streamlines close to its dissociation point always. And this is a temperature here and here. So this implies the flows are subsonic in molecular winds. As Selina said, yes, they are subsonic and very slow. If we want some supersonic, very high velocity molecular winds, we need very much high FEV luminosity, which may be unrealistic in the standard view. And I showed, my model predicted FUV-driven molecular photoevaporative winds, but similar results are obtained in the context of X-ray-driven photoevaporation and external FUV photoevaporation. So there are somehow model dependencies, but I think we can expect molecular photoevaporative winds. And there's one caveat for FEV-driven molecular photoevaporative winds. They depend on the small grain abundances. In my study in 2018, I varied metallicities of the disk, and I only saw molecular flows. I mean, I couldn't see the molecular photoevaporative winds in the lowest metallicity case. This is simply because the amount of small grains, which is the main contributors to FEV heating, is very low. So it slows photoelectric heating. So it's FEV photoevaporation. So this very low metallicity could be achieved if we take into account grain growth, for example, or dust settling to the midplane. And if dust to gas mass ratio somehow decreased in the disk by, for example, radial drift or something. So yeah, there are a lot of scenarios when it comes to FEV-driven photoevaporation depending on the small dust abundances. So it's important to consider about dust properties of the disks for the FEV-driven photoevaporation. And
sorry, you mentioned it's small dust abundances. It means the dust abundances are small. or it's the small grains abundance?
Yes, small grains abundance. So abundance
Okay.
of small grains like grains less than 10 nanometer or something, including the PAHs. Yes. Thank you for the clarification. That's very important. And this result is a key for the second part of my talk. So please keep this in mind for a little. And finally, I mentioned about observation of molecular winds. And it's known that H2 infrared emission have blue shift, moderate blue shift, and it's known to be consistent with X-ray photoevaporation model. Also, could also be MHD winds indicators, but anyhow, X-ray photoevaporation could reproduce the line profile of this infrared H2 line. And I think FEV-driven photoevaporation, as in my model, can reproduce this line profile of infrared H2 by comparison between X-ray model and my FEV-driven model. And I'm working on post-processing of my hydrodynamics model in collaboration with Christian Lab in Munich now. But I don't get any result, sorry. And as for CO molecular winds, it's observed through infrared and sublimeter observations. And in a disk, CO is also known to have a blue shift line, and it's usually concluded as MHD-driven winds. I kind of agree with that result because, as I showed, I think driving extended CO photoevaporating winds are relatively difficult in terms of photoevaporation. But the Thomas Howard's model pointed out CO winds could be excited in the context of, in terms of external photoevaporation. And at least it could reproduce the sub-millimeter observation of CO winds. So
Yeah, that only CO actually carbon line as well. Carbon 1 wind.
carbon one?
Yeah. It can be very, very good tracer in our external
Right.
wind.
Yes. Thomas.
Thomas model.
Yeah, in 2020.
That's right. And I have a question that the molecular hydrogen is that two components over there?
I think. This.
Yeah,
two
tau.
components. Yes.
And the velocity is about, okay. That's very detectable velocity, right? Yeah. 1 kilometer,
But
0.5 is tough, but
with JWST, we have spatially resolved H2. I was sure
Okay.
oh.
they are really extended.
So in externally driven wind, there is a JWST image and also actually Muse images where those lines are, they are actually spatially resolved.
Oh no. Interesting.
Yeah.
Okay, then sounds like it can compare directly with hydro simulations probably. And if it's reproduced.
I am observing some in infrared. That's why I was looking at it because I'm going to get some data of. I'm going to see the H2. I was looking at that.
I found both H2 and CO winds are interesting. And I think for now, as for CO wind, I think it's better not to rule out the possibility of CO winds by photoevaporation completely. And there are some model dependencies in conclusions. Okay, this is a summary of part 1, and I saw H2 photoevaporative winds in my self-consistent simulation thanks to the advection, which could be incorporated only in self-consistent modeling. And H2 flows have extended structure at the radius of larger beyond 50 AU with lower temperature right here, and a slow velocity. And the H2 molecules can survive for photodissociation timescale after its launch. And the one caveat is FUV-driven winds are inhibited in small grain depleted disks. This result is related to part two work.
So before you go to part two, so there's a Peter Pan disk, like endo, those kind of endo star, low mass star, and those are refused to grow out. So my first naive question is, does the photoevaporation apply to those disks?
I actually had the same question, so I wanted to talk to you about this.
Okay.
Or interesting point.
Yeah. So what do you think?
I mean, these objects are 50 million years old.
Yeah, they're old.
And they are accreting.
They're 30 and 50 million year old, and they still have a accretion disk.
Okay, so sounds like as a discussion.
Yeah. Discussion.
Okay, and then the second question is, if a disk, I don't care what it is, there's how old, if the disk, they have no submicron grain, will photoevaporation work at all?
No what?
No submicron, small grain. If there's no small grain at all, does photoevaporation will work at all?
Photoevaporation, FUV photoevaporation doesn't work. But
Okay.
EUV
Yeah.
X-ray photoevaporation works because
It's just in there by
hydrogen.
the gas. Okay,
Yes.
right. Good. Okay, sounds good.
But in X-ray, when you're talking about that X-ray, is like hard X-ray, right? Not the soft. Is it soft X-ray?
Yes. Hard X-ray
It penetrates through, basically.
penetrates through and
Yeah.
it
It
doesn't
doesn't interact much.
to heating. It doesn't.
Yeah, but the soft X-ray between 0.1 and maybe 1 kb.
0.1 kV to yes,
Yeah,
1 kV.
okay.
Say, yeah.
There is a question online.
Oh, yeah. Since you mentioned that molecular hydrogen can be created in MHD winds, would you expect a difference in a special location of H2 between the photoevaporated wind scenario versus MHD wind scenario?
Yes, I mean, photoevaporation cannot be driven from the radius within the gravitational radius. So if we observe, if we trace H2 winds from the inner radius, like less than 1 AU or 10 AU, then it should be MHD winds. But I don't know the method to differentiate between photoevaporated winds and MHD winds excited from a larger distance of the star, like 10 AU or something.
What about 300 AU?
Yeah.
300 AU. I would say photoevaporation, but maybe biased if
Vertically, not radial.
Yeah.
vertically, not radially. Yes, still photoevaporation can be possible too, but excited particle.
But the external photoevaporation works great at that outer radius. And
Yeah,
a pretty low FUV field.
even pretty. Yes,
I mean, not pretty low, meaning here, not like ONC, but like hundreds of maybe.
hundreds. Yes.
Yeah.
Then it could.
Is it?
Yes, it could work.
But then, can you tell from if you have a super good resolution of spectroscopy, maybe the line width would be different for MHD wind and the photoevaporated wind? Photoevaporated wind, I would expect it very narrow.
At the distance.
Would you expect that the MHD wind to be wider than photoevaporated wind? Yeah,
Yes.
yeah.
I mean,
So it'll be more like, broadened for the MHD wind if you can detach that. Yeah, but.
yeah. Radially touched that. But I always wondering like if MHD winds are excited from outer distance, like beyond 10 AU, can we distinguish photoevaporated wind by MHD?
Probably
Something I
not.
ask.
I don't know. We should ask you, actually. I should.
Yeah, I mean, only so that we could test would be temperature, right? Photoevaporated winds are pressure driven, so it always needs high temperature.
Yeah.
Beyond higher than disk surface, I mean disk part. So if we could get temperature information, then we can see.
So different, depending on which tradition, you could tell temperature dependence there, maybe. If you have line from the different tradition of the atomic level, that then you can actually
That's-
see higher temperature than the lower temperature.
Yeah.
So,
Yeah, I have a question about photoevaporation, external photoevaporation as well, just because I typically work with objects that are much younger and have much more gas and dust and optical depth in the disk, but it seems to me that external photoevaporation for the scenario that you're talking about should depend somewhat on the inclination angle between the external source and the disk. So would you expect sort of asymmetric morphologies to the winds depending on how, is it face on to the evaporative source, or is it,
I see.
but again, I'm thinking in a world where you have very high optical depth in the disk itself, so.
Yeah. Well, yeah, it should depend on the distance, right? If it's too far away from the source, then maybe there's negligible
Yeah,
asymmetries. But if it's close, then maybe closer side have more
right,
a higher temperature than distant side of the disk.
right.
Yeah, that's an interesting question. Maybe it may also dynamically affect to the disk, probably. Like photoevaporative winds can exert a repulsive force to the disk itself, so it can affect the inclination of the disk, probably. And well, it's my guess. Yeah, so. Is there any other questions?
You answered that.
Okay. So, so future prospects. I think few follow-ups are needed with a more detailed chemical network, because including this reaction is important. This reaction could destroy its molecules in high temperature regions. So it's maybe vital. And post-processing of the radiation hydrodynamics models are important. It's ongoing, as I said, and thinking about JWST and the post-observability by JWST and target selection would be interesting. And also it would be interesting to think about how to disentangle the photoevaporative winds and emerging winds. Oh,
20 minutes left.
20 minutes left.
Yeah, you gotta,
Okay, I'll try.
you gotta run.
Oh no. Okay, I will go to the second part. So I introduced classically gas disks are thought to dissipate within 10 million years. So after that, disks are supposed to be gasless. But recently, very old gas disks are detected in more than 20 sources. This is called gas-rich debris disks. The gas origin is unknown, and one of the hot topics in the field now. And I think it's particularly interesting because this could be an intermediate object between PPD, protoplanetary disk, and debris disk. So it should have a key to understand the dispersal process, evolutionary process from protoplanetary disk and debris disk. And for the origin of the gas, two hypotheses are proposed. One is primordial origin scenario. This explains the gas to be a long surviving protoplanetary disk. But as in the first part, this scenario has been ruled out because observations suggest 10 million years lifetime, less than 10 million years lifetime. And some theories, some models suggest less than 10 million years lifetimes for gas. So people are more interested in secondary origin scenario. This scenario tells gas is released from planetesimals, colliding planetesimals in planetesimal belt. So it accumulates the gas to be observed as gas-rich debris disks. So the primordial origin scenario was ruled out practically, but in 2021, I came up with the idea to make this scenario possible. So I'm going to talk about it later. So before going to my model, I introduced these three interesting observational facts. It is known that CO-rich systems have high CO mass to dust amount, resembling protoplanetary disks. So it's similar to protoplanetary disks, but not like planetesimals or comets or asteroids. So this was problematic because it needs unrealistically high production rates if we assume secondary origin scenario is the origin for these gases. And another interesting fact is gas-rich debris disks are often detected around young age stars. Right, so young means less than 50 million years. And the other interesting fact is typically asymmetric gas disks have a extended radial distribution compared to dust disks. So it's surprising because co-location between gas and dust are expected if we assume these gas and dust are coming from secondary origin. Anyhow, these characteristics are important because it gives hints to understand the origin of the unknown source of the gas. And this step summarizes whether secondary origin models and primordial origin models explain the observational facts obtained so far. The starting point is, of course, the old age. Secondary origin model is easy to explain it because it can produce gas as long as there is planetary belt. And the primordial origin scenario was thought to be no, because of the observations and theory. And secondary origin models have been developed extensively, and they hit the walls to explain several observational facts, but they managed to come up ideas to explain those observational facts after all. Now it seems like secondary models are struggling with over prediction of atomic carbon mass. And later in 2021, I come up with an idea to extend the disk lifetime. So, and after that, follow-up studies have shown that these observational characteristics can be explained in the framework of primordial origin scenario. So previously, secondary origin scenario is the most likely and only possible scenario to explain gas-rich debris disks, but now the thought is changing, like both scenarios may be possible. And here, I'm going to explain why I thought primordial origin scenario cannot be ruled out. This is canonical photoevaporation rate and corresponding dispersal timescale. And this timescale is used to rule out the primordial origin scenario. But this canonical photoevaporation rate is estimated for solar type star and relatively young system. But intermediate mass stars can reduce the EUV and X-ray luminosities according to the stellar evolution, like this. So intermediate stars loses their convective zones to drive the magnetic activities needed for strong EUV and X-ray radiation. So after losing the convective zones, the intermediate mass stars reduces their X-ray and EUV luminosities. This is one of the reasons why primordial origin scenario would be possible. The second reason is reduce the FUV photoevaporation, as I explained in the part 1 talk. The main contributor of FUV heating is small grains, including PAHs. And this abundance could be reduced if we take into account grain growth like this, right? So FUV photoevaporation is known to produce this high level of mass loss rates, but if we take into account small grain depletion due to grain growth or other mechanisms, then photoevaporation rate, FUV-driven photoevaporation rate should decrease. So in summary, all of FUV, EUV, and X-ray photoevaporation rates can reduce around small grain depleted disks. of intermediate mass stars. Okay, so this is the reason why primordial origin scenario could be possible. And I tested my idea with running hydrodynamic simulations for small grain depleted disks around 2 solar mass stars. And left side show the disk with ISM composition. So they have small grains. And on the right, I assumed a fairly evolved disk, and it has a small grain depleted state. The mass loss rate, left side mass loss rate corresponds to this one, and right side mass loss rate corresponds to this line. So as you can see, mass loss rate is significantly reduced by the effect I talked in the previous 2 slides. So I concluded photoevaporation rates are slowed down around small grain depleted disks around intermediate mass stars. And I estimated the dispersal timescale like this, longer than 10 million years. And in more recent model, I explicitly calculate the mass reduction of small grain depleted disk, including the effect of MHD winds, viscous accretion, and photoevaporation, with incorporating stellar evolution. This is the mass loss rate as a function of stellar age. As you can see, the mass loss rate of intermediate mass stars sharply drops like this after convective zones disappears. Then these are disk mass evolution as a function of time. For solar mass stars, mass loss is dominated by MHD winds, and it switches to photoevaporation after a few million years, owing to a relatively high photoevaporation rate. And disk mass sharply reduces after photoevaporation dominant epoch comes. For intermediate mass stars, the MHD disk wind dominant epoch extended toward longer edges, and switching point from the MHD wind dominant epoch to photoevaporation dominant epoch comes very late phase. So in short, thanks to the reduction of photoevaporation rates around intermediate mass stars, primordial disk can survive for longer than 10 million years. And I compare, this is the obtained disk lifetime as a function of stellar mass. I see the peak lifetime is here at the 2 solar mass or something, corresponding to early A type or late B type. And for low mass stars, they have convective zones throughout disk evolution, so they can keep high photoevaporation rate throughout the disk dispersal. So lifetimes are short. And for higher mass stars, they actually lose the convective zones earlier than the low mass intermediate mass stars. But they have a high photospheric temperature, so they can have strong photospheric EUV. That's why for the disk lifetimes are shorter than these A-type stars. And this is the observational occurrence rate of gas-rich debris disks. And these two are qualitatively consistent in 3 aspects. Like first, A-type star has the highest incidence, and the incidence decreases toward earlier and later type stars, which is also consistent with this model. And even at the A-type star, the incidence decreases to older ages. So it indicates somehow gas needs to be dispersed, whatever the origin is. So I found this qualitative agreement is interesting. So anyhow, this also shows the primordial origin scenario is plausible in contrast to the previous thought. So more investigations are needed observationally and theoretically. And I'm finalizing my talk with mentioning future prospects about this study. The first one is gas disks around young A-type stars without dust emission. We name it a phantom disk. So currently, only gas surveys are only performed for dust bright disks. But if we look at young A-type stars without dark dust emission, then we may be able to detect gas disks, long-living gas disks, because primordial origin scenario allows it. And it may be interesting to consider about possible links to the gas giant occurrence as a function of stellar mass. As in our model, the gas giant occurrence peaks around 2 solar mass star. Then if we assume the gas giants are easier to form around in longer lifetime disks, then higher occurrence may be achieved, but more investigations are of course needed. And our results may be also relevant to the higher occurrence of transition disks around Havoc stars. So yeah, this is a topic of the future investigations, I think. This is the last slide. So main message of the second part of my talk is primordial origin scenario could be possible. So more investigations are needed from theoretical and observational point of view. And yeah, and the important thing is that I'm not trying to rule out the secondary origin scenario. Personally, I think both scenarios are possible for now. So it's also important to differentiate which origins are most likely for respective individual sources. That is a future work. Okay, maybe that's it. Thank you for
Question?
One for the second part. So what is the expected mass accretion rate on these intermediate mass stars, and can it be measured?
At which part? At which space? Like
I mean, you say that maybe some of these, what we call debris disks, are primordial disks. So then they would be accreting disk gas, right? So what would be the rate?
Yeah, so in this model, I didn't solve the 1D radial distribution, so I cannot say specific thing about accretion rates, but so accretion, it's not.
But you have the mass loss rate from the wind, right? So the mass accretion rate must be higher than that.
In this model, I explored a lot of parameter space. Like sometimes it has a higher accretion rate than winds, and sometimes wind has higher mass loss rates than accretion. So, but anyhow, the lifetimes are the longest at 2 solar mass stars, and it doesn't depend on how long accretion continues in the early phase. So
I was just thinking that one way to check if they are primordial is to measure accretion of gas onto the star, but I don't know if it's possible.
It's not measurable. There's no H alpha. Most of them there's no H alpha.
Right.
Right. So I think you got the point. The accretion rate must be higher than the whatever the rate. So which has to be 10 to the minus 10 something or higher.
Measurable.
And it's measurable, but it's not
Yeah. When in the past I was checking for accretion in debris disks and I didn't find any.
No, there's no.
But there is a very strong photospheric absorption, and so maybe we are not able to remove it at the level to find some excess.
Yeah.
Yeah, for us, yeah.
But I'm pretty sure that you can do that with, you don't have to do H alpha, you can do hash alpha, whatever
Right.
you lower that was more sensitive to the accretion rate, to the
Or was it
lower
down?
accretion rate. No, I don't know whether it's down or not, but I'm not aware of any detection.
Okay.
Yeah, to follow on that question, so yeah, it sounds like more massive star can have lower photoevaporation, they can have their time longer, but they're still primordial. They should be dominated by H2, right?
Yeah.
So how do you explain the CO, mostly the gas we detect in this kind of debris? These are all, CO dominated. We don't detect any H2 on it.
No, not so far. We don't. No detection for H2 or other molecules.
Yeah, exactly. So that means the gas composition is not the same as the primordial.
Very, very low.
Could be, or so H2, and yeah, the gas temperatures are quite low. So I didn't check by running post-processing calculation, but I'm not sure if H2 can produce a detectable emission from the gas disk.
Okay, so
I
you were
don't-
talking.
Probably interesting actually to do.
Yeah,
Yeah.
And infrared.
it's like it's coming from outer distance from beyond 10 AU or something. So, I mean,
Yeah, fine. We don't have far infrared. Otherwise, you can detect, I don't know, the C2, whatever, all those cooling things,
Right.
right? But that's some calculation should be done. I mean, to me, the second generation gas is the most driver is really just like you see the abundance so different from primordial gas, mostly dominated by carbon, oxygen,
yeah.
not hydrogen, basically.
But I mean, the reality is that when we detect H2 at infrared wavelengths, we don't detect the bulk of the H2.
Yeah, you get the
Even
surface
young
only.
disks,
Yeah.
so it's not clear that we are, I mean, we think we are dominated by H2, but we actually don't know.
What are the typical
So-
temperatures of the gas disks detected in CO?
Detected in CO, like 70 Kelvin at
Okay,
highest, if I remember correctly.
okay, so that shouldn't be.
There's a question online. Sorry. Norman, would you like to unmute and ask question?
Yeah, sure. I was just wondering if you go to even higher mass than the intermediate stars, would you expect to see any high mass gas-rich debris disk, or would they have then enough photospheric UV or XUV to disperse?
Yeah, I think they have very short lifetime, like this figure shows. They have a strong photospheric EUV emission, and maybe some old type star could have soft X-ray emission from line-driven winds. So I expect even higher masters have even shorter lifetimes.
Interesting. Thank you.
Thank you.
Okay, listen. Yeah.
Okay, sorry. I'm just letting Josh know I'll be late for our meeting.
John, you should call it.
Anyway, so my question, I've two sort of related questions. You said that there are multiple scenarios for how a disk could be depleted of small grains, and one of those scenarios was grain growth. Have you compared or modeled the timeline of grain growth to the point that photoevaporation is hindered compared to the time that it would take to evacuate the disk of gas? Are those timelines compatible? Is that?
Yeah, according to dust evolution scenario, for example, performed by Selek et al. 2020 and other related simulations, dust growth is quite efficient, like less than dust type growth time scale is less than 1 million year within 100 AU. So I think so that's quite shorter time scale than the lifetime or whatever the time scale of the needed for photoevaporation to dominate the mass loss. So yeah, I think small grain depletion can happen within reasonably short time scale.
But not just for photoevaporation to dominate the mass loss, but for the gas to be totally depleted.
Right. Yes. So 1 million years is kind of the scale.
Okay.
That's good.
And then the other question I had is, have you considered looking at this process or part 2 of your talk for disks around maybe lower mass stars that are nearby to a very high mass star, like an OB star, which I ask for purely selfish reasons because I have a project coming up in a maybe 6 months, looking at disks that are in very strong UV radiation fields. And I know that previous work, my advisors, one of my advisors' grad students found that disks in Orion that are very close to the trapezium, disks around low mass stars that are nonetheless in the UV field of the trapezium, are they have a much higher gas to dust ratio than field disks, and they're sort of bigger and puffier. And so I'm wondering if that could be a scenario that might lead to a longer lived gas disk, just because the gas might protect the dust, allow more grain growth to occur more quickly or something like that.
I see.
Well, in Orion case, actually, that's because the external field is really hot, but the gas doesn't freeze out.
Right. I know why the gas isn't freezing out, but I'm wondering what the effect would be on the
That
disk.
could apply here.
Yeah.
Definitely. I was thinking about that too.
Yeah.
I was thinking about the same thing, like that's happening. There are higher gas actually taking a smaller truncated small disk than the big disk. And the reason is because it is hot and they were not freezing out. Basically, that could be happening around the A star, for instance.
Yes, but in that case, instead of the host star being the A star, it's you have a K star minding its business over here, and then an O star some distance away.
Right.
So,
but around the A star, at large because of A star itself is hot actually.
Right.
It could apply there.
Right. So, but you said for the most massive stars, the Bs and the Os, they have they're much hotter.
Yeah.
So for a disk around those stars, you wouldn't get, like, obviously the gas would be depleted because they're very hot. But if you had some other source that was further away where it's cooler and they have that weaker field, I was just wondering about the effects of that.
Okay.
It's gotten a little complicated, and I do have to run to another meeting. But yeah, Serena will know
I mean, I should talk to you about that.
Yeah.
He's here for a week.
Okay.
Yes.
You can email and then we can meet actually then. Okay. Thank you.
Interesting.
Yeah.
There is a person.
There is. Oh, yeah. There is okay. Go ahead, please. Okay, Kelly.
Hi, sorry, I don't mean to interrupt. I know someone said that they had to get to another meeting, but I was just curious, and this probably will be answered either in the presentation that I wasn't paying attention to or in a different part of the study. But how does the size, the density, and I mean the quantity of what's in the dust in the disk affect the actual star itself? I suppose, simply put, like, why is it a concern, if it is a concern, or is it just the quality of the disk that exists around the stars?
Sorry, what is the question?
Yeah, could you rephrase?
I guess for the shorter version, for a longer question, why is it important to know about the quality of the disk and how the stars around them react to it, I suppose is the correct wording?
Maybe it's related to the fact that you mentioned that you need small grains to evaporate them, so that you need to know better the disk properties, right?
Right.
To understand if photoevaporation is.
Yes.
Maybe you can.
What was the question actually?
I think she was wondering why it's important to know the properties of the disk for this study. And maybe she missed that you said that it's important to know in particular the amount of small dust grains.
Okay. Thank you. Okay.
I think, I'm not sure.
Okay. So.
Okay. Yeah. I just missed it.
Okay. So yes.
Yeah.
This simulation shows small grain. If disk has small grains, then it can produce higher photoelectric heating rate because they have the main contributor of FUV heating is submicron grains and PAHs. But if small grains are depleted, like in this on the light movie, then massless states only gets like this. So that's why small grains are needed to heat the disk efficiently.
Okay,
FUV heating. Yeah.
thank you so much. I definitely just missed it in the presentation. You answered my question perfectly.
Okay,
And thank you
guys.
for explaining my questions back. That made a lot more sense than what I was saying.
Sure. Thank you.
This was a great presentation.
Thank you.
All right, let's thank again and then we'll talk to you more in person. Yes.
Yeah.